In this chapter, we are going to acquaint ourselves with a few algorithms that are based on the divide and conquer design strategy. We have already encountered an algorithm that is based on the divide and conquer approach, namely merge sort. If you remember, when we discussed merge sort, we saw that the overall problem of merge sort was solved by dividing the problem into two subproblems, recursively solving those two subproblems, and then combining or merging the answers to those two subproblems to create the solution for the overall problem. And we saw that such algorithms have three steps. There is a divide step where we divide the overall problem into subproblems, and by subproblems we mean here a smaller instance of the same type of problem. For example, if the overall problem is of sorting an array of size n, then the two subproblems that we created for solving the overall sorting problem in the merge sort algorithm was to sort an array of size n by 2. So there were two subproblems created from the original problem. And the subproblem was just a smaller instance of the same type of problem. So it was just a smaller instance of the larger sorting problem. So in the divide step, we divide the overall problem into a bunch of subproblems. Then we recursively solve or conquer the subproblems. If the size of the subproblem is large, sufficiently large, then we recursively solve the subproblems. That is, we again divide the subproblems into even smaller subproblems and then try to conquer them recursively. But if the size of the subproblems is small enough, then we can solve the subproblems directly without recursing them. For example, in case of merge sort, when we bottom out the recursion to end up with a subproblem of size 1, then we don't need to divide that subproblem further. We can directly solve for that subproblem. And we don't really have to do anything there because an array of size 1 is by default already sorted. So that's where the recursion bottomed out for merge sort. And then in the third step, we took the answers or solutions to the subproblems and we combined them to create the answer to the overall problem. In case of merge sort, once we had two sorted subarrays of size n by 2, we saw how to merge the two sorted arrays into the larger sorted array, into a merged array, which was the sorted version of the overall problem. We saw a linear time merge procedure for that. And that was the combine step, where we combine the answers to the subproblems. So these three steps appear in any general divide and conquer based algorithm. So, assuming that the original problem is of size n, the divide step could divide the problem into a subproblems in general. In case of merge sort, the value of a was 2. And each subproblem may be of size n by b. Again, in case of merge sort, the value of b was 2. The divide step divided the overall problem into two subproblems, each of size n by 2. Combining the answers to the subproblems may take time proportional to or time equal to some function f of n. So in case of merge sort, this f of n was c times n. And if you have two sorted arrays of size n by 2, the amount of time it takes to merge those two arrays into a larger merged array of size n was proportional to n. So in general, if a divide and conquer algorithm splits a subproblem into a subproblems each of size n by b, and if it takes f of n time to combine the solutions to those subproblems, then the overall running time for an input of size n can be stated as T of n, which is equal to the time it takes to solve a subproblems each of size n by b, plus the time it takes to combine the answers to these subproblems into an answer for the overall problem. So T of n therefore can be written as a times T of n by b. T of n by b is the time it takes to solve a problem of size n by b. And because there are a subproblems of that size, the amount of time it takes to solve a subproblems of size n by b is a times T of n by b. And then it takes f of n time to combine the solutions to these a subproblems. And so the running time on an input of size n is given by a times T of n by b plus f of n for a divide and conquer algorithm. For merge sort, T of n was twice of T of n by 2 plus c times n. So a was 2, b was 2, and f of n was c times n. We are now going to look at a bunch of examples of recurrence equations of this sort to familiarize ourselves with how we can go about solving such recurrence equations. So we are first going to take specific examples of such recurrence equations, a variety of examples, and then we will try to come up with a general solution to a problem that is based on the divide and conquer design strategy, whose recurrence equation in general is of this form. T of n is a times T of n by b plus f of n. Here's the first recurrence equation we're going to look at. T of n is 3 times T of n by 3 plus c times n. Now one way to think of a problem whose running time is given by this recurrence equation is merge sort itself, where instead of dividing the overall problem into two subproblems, let's say we divide it into three subproblems, each of size n by 3. So we take an array of size n and we create three arrays of size n by 3 by partitioning the array equally into three parts, and then we solve or sort each of those three sub-arrays independently, and then we combine the solutions to those three subproblems into a solution to the overall problem. And we can easily do that by modifying the straightforward merge sort pseudocode that we saw earlier, where instead of using two pointers pointing to the heads of two sorted arrays, we will now use three pointers pointing to the heads of three subarrays. And the merge the merge procedure will be very similar to the one that we've already seen, except that we're going to now use 3 pointers instead of 2. So in each step, we will be comparing 3 values and incrementing the pointer that is pointing to the least of those 3 values and appending the least of those 3 values to the merged array. So we can extend the pseudocode that we saw for the merge sort algorithm to divide the overall problem into 3 subproblems instead of 2. Likewise, you can imagine dividing the overall array into 4 subproblems, each of size 1/4 of the original problem, and so on. So the question is, does it matter how many subproblems we divide the original problem into? Well, if we solve for this recurrence equation, we'll be able to know whether it matters whether or not we divide the overall problem into 2 subproblems or 3 subproblems. And let's try to solve this recurrence equation using the recursion tree method, the same method that we use to solve the recurrence equation for the merge sort algorithm, where we divided the overall problem into 2 subproblems. We'll do that in the next video.